Well, previously we talked about the effect of temperature on the fate of the reaction in which addition is taking place on an alpha beta unsaturated carbonyl compound. This time we will talk about the structural factors that affect the overall outcome of the reaction. The structural factor primarily means the reactivity of the carbonyl group. So if the carbonyl group is more reactive, it will favor direct addition. And direct addition, is the reaction in which the nucleophile attacks the carbonyl carbon. But if the carbonyl group is less reactive, then conjugate addition is favored. This, in other words, mean that if the carbonyl group is more reactive, it means the carbonyl carbon is more electrophilic in nature, and that will have more affinity towards the nucleophile, leading to a direct addition product, while a less reactive carbonyl group has a less electrophilic carbonyl carbon, and that is why lesser affinity towards the nucleophile, and that is why conjugate addition is favored in that case. So the reactivity order of the different carbonyl groups is given here. So we have an acid halide, an aldehyde, a ketone, an ester, and an amide. And all of these carbonyl groups are alpha beta unsaturated. So you can see that they are arranged in an order in which reactivity increases when we move from amide towards acid halides. I hope you all know why this order is so, but let me briefly discuss it here again. So starting with the acid halide here, you can see that it's the most reactive of all the carbonyls given here. It is because of the fact that we have an electron withdrawing group attached directly to the carbonyl carbon. So inductively, this chlorine atom is electron withdrawing, that increases the electrophilicity of this carbonyl carbon, making it more reactive towards the nucleophile, and so it will favor direct addition. You would be thinking of the lone pairs on chlorine being involved in resonance with the carbonyl, but you know that in halogens, like in chlorine, this resonance is not much effective. So inductive effect here dominates, and that increases the electrophilicity of the carbonyl carbon. Then comes the aldehyde. Aldehyde has a hydrogen on one side of the carbonyl, and so it does not have any electron donating or electron withdrawing effect. But when we move on to a ketone has an alkyl group here, like a methyl group here in this case on the left hand side, that donates electron density to the carbonyl carbon, making it less electrophilic and less reactive towards a nucleophile. So comparatively, aldehyde is more reactive as compared to a ketone. Then comes the ester. Now, in ester, you know that we have an alkoxy group here attached to the carbonyl carbon. Inductively, this oxygen is electron withdrawing, but oxygen also has lone pair which can be involved effectively in resonance with the carbonyl group. So that resonance is more effective in this case than the acid halide, and so it decreases the electrophilicity of this carbonyl carbon, making it less reactive even from the ketone. And finally, we have the amide, in which we have a nitrogen atom attached directly to the carbonyl carbon. And as you know that when you compare oxygen and nitrogen lone pair is more available for resonance with the carbonyl carbon. So the electrophilicity of the carbonyl carbon here is decreased more, and so it's the least reactive of the given carbonyl groups. So when we talk about the reactivity, acid halides would happily go for direct addition, while amides and ester will go for conjugate addition. So let's see this with the help of some examples. If we have an aldehyde and we react it with butyl lithium at minus 70 to 20 degrees centigrade, this is what we get as a result. And so from the product, you can see that it's a direct addition product in which the butyl anion attacks here at the carbonyl carbon, forming an alcohol here, and butyl group is attached to the carbon which was the carbonyl carbon of the aldehyde. Under the same conditions with the same nucleophile, if we have an amide here, then we will have conjugate addition. So you see that this butyl group now is attached at the beta carbon, which means that beta addition, which means that conjugate addition has taken place here. And that is because of the less reactivity of the carbonyl group in case of amide, although rest of the conditions are very much similar. If we have an acid halide and you react it with ammonia, again, because acid halides are very reactive and they will go for direct addition, this ammonia attacks the carbonyl carbon of the acid halide, and this carbon, when it collapses back, we have a chloride ion released as a leaving group. So the acid halide is then converted into an amide, making it less reactive carbonyl towards addition reaction. If we have an ester and you react it with the same nucleophile, that is ammonia, because esters are less reactive as compared to acid halides, this ammonia will attack the beta carbon, giving you this ester having its NH2 group at beta position. So in the first case, direct addition takes place, which removes chloride ion as a result, while in the second reaction, it does not happen at the carbonyl carbon, but it happens at the beta position. So the ester group is intact. Here we have an aldehyde reacting with sodium borohydride. Sodium borohydride, is a reducing agent. It's a hydride transferring reagent. So the first question to ask is, where will this hydride ion be transferred, whether at the carbonyl carbon of the aldehyde or at the beta position, which also is electrophilic in nature. So looking at the product, you can see that the hydride group has been transferred to the carbonyl carbon of the aldehyde, making it an alcohol, reducing it to an alcohol, which means that because of the higher reactivity of the aldehyde, carbonyl carbon direct addition has taken place. Under the same conditions with the same nucleophile, if we have an alpha beta unsaturated ketone here, you see that both the double bonds and the carbonyl group are reduced. But if we have an ester, only the double bond is reduced by sodium borohydride. So this shows the reactivity of the selectivity of sodium borohydride towards an alpha beta unsaturated aldehyde, ketone, and ester. In case of ester, only the double bond is hydrogenated and the ester remains intact. In case of ketone, you know that both the double bond as well as the carbon group has been reduced, while in case of aldehyde, only the aldehyde is reduced to an alcohol. Another major factor, apart from reactivity of the carbonyl groups, is that of steric hindrance. So if a carbon atom, which you think is electrophilic in nature, has some bulkier groups attached to it, that will offer steric hindrance to the incoming nucleophile. So the nucleophile will avoid attack at that position. A less hindered position will be attacked more easily and more frequently. So if we have these three alpha beta unsaturated ketones, you can see here that the beta position has two hydrogens. Here the beta position has a methyl and a hydrogen, and here the beta position has two methyl groups. So if we have a nucleophile and the reaction conditions that will favor conjugate addition, the conjugate addition will happen more easily at this alpha beta unsaturated ketone, because here the beta position is unhindered, while at these two it will be less probable. So steric hindrance also plays a vital role in deciding which product will be formed in higher percentage. So these are some of the structural factors that may affect the overall fate of the reaction and leading the reaction towards a direct addition product or a conjugate addition product. We will discuss the effect of the nature of the nucleophile in the upcoming session. Thank you so much for now.